All right, hi everyone. Hopefully you can hear me well. Thank you so much for a kind introduction, Pete. I'm Diana. I'm the head of machine learning of Kensho, S&P Global's Innovation Hub, and today I'm going to talk about building blocks of tomorrow from AI-ready data to agentic systems. A little bit more about myself. My current role, I've been leading these teams for 3 years now, but before that I spent about 5 years at Capital One heading up the conversational AI department. At Capital One, we launched the first banking assistant in the US. It was quite revolutionary back in those days. It was called Eno. It still exists until today. However, most of my team, unfortunately, is gone from there and moved on to the new roles. And before that, I was an engineer at Nuance Communications. We were building conversational AI systems for mobile markets and for automotive for some of the biggest customers across Europe and United States. And Nuance back in the day was a pioneer in conversational technology overall. So it was amazing for me to witness the evolution of conversational AI and where we started from and where we got today with that technology. Now, a little more about Kensho. Kensho was a fintech startup. It was acquired in 2018 by S&P Global. And ever since then, they, I think, did a really good job in not merging the startup into the bigger company, but keeping it independent. So we are able to continue moving fast as a startup, continue exploring cutting-edge technology and really introducing it and helping the bigger organization to adopt and integrate it into all of their platforms and solutions. And about S&P Global, I know it's a very big and famous company, but I think many people know only certain aspects of S&P Global. The company has more than 160 years of history. There were multiple mergers and acquisitions, but they were always focused pretty much on the data collection and data analysis and insights for financial markets. They've been known for more than half a century as McGraw-Hill's Financial. But in 2016, they adopted the name of S&P Global, and since then, we are known under that name. And a little more about areas of operation of S&P Global. Unlike a typical financial institution focused on loans, banking services, or investment and trading, S&P Global really operates as a global provider of essential intelligence across financial markets all over the world. And there are a number of divisions combined under the roof of S&P Global. We currently have 5. One of them is being spun off into a separate company, but the rest of the 4 are on the slides. First of all, very famous S&P 500 index, among many other indices that S&P Global produces. Then there are ratings that we assign to many entities, including the countries. Then there's also market intelligence, a very big division that is responsible for data collection and data insights on global market. And there is commodity insights that is focused on benchmark prices and information on the commodity supply chains and energy markets. And in terms of our customers, those are typical financial institutions mostly, but also large corporations that need access to this type of data that we collect and sell. And one last note on this slide, we have a new CEO. She stepped into her role a little bit less than a year ago, Martina Chong. And she is laser focused on uniting the enterprise and uniting those verticals under the same common mission and really creating much smoother customer experience. So customer doesn't need to know about the organizational complexity of the big mothership, but really interacts with the customer, with the company as a unified experience. So in that journey, AI is essential because AI technology really helps transform the company in these horizontal ways and connect different divisions together under the same technology strategy. And this is where Kensho is really leading the way and helping company transform itself with AI. All right, and now let's start with AI-ready data. It's the beginning of everything. It's the foundation of any complex agentic AI technology that exists today. And I, first of all, wanted to talk a little bit of what do we mean by AI-ready data? You probably hear these words everywhere. A lot of different people use this phrase to describe different things. And I want to be crystal clear in terms of what I'm referring to by AI-ready data. AI-ready data is data that has gone through a certain amount of transformations, and certain things were added to the data structures and data sets to make it readily available for large language models to interact with. And the two big types of the data that we are really dealing with is tabular, which we call structured, so it's your relational databases, and unstructured, that is in our case mostly textual, but in some other cases it could be graphical, video, audio information, and anything else that is not really clearly put into a table and curated and cleanly represented in the databases. So those are the two main types of data. And when we talk about those transformations that need to happen to the data to make it available to large language models and Gen AI, when it comes down to tabular data, it's really making sure that one thing that you need to understand is that large language models, they interact with your data in natural language. So they need to understand what is stored in the database. And a lot of column names, table names are not very descriptive, especially with old databases that 50 years old and have been grown for decades and got very different, very complex structures, a lot of tables, a lot of relations between the tables that are not documented. So it's a very hard problem to solve. So the number one thing that you need to do to prepare your tabular data for LLMs is to make sure that you attach rich metadata to those tables. And that includes description of the schema. It includes foreign key relationships that normally should be described within the database, but only if you're very diligent and stick to the rules of best practices of how you create those databases. Unfortunately, in the reality, it doesn't happen a lot. So a lot of work needs to be done to describe the tables, make sure the schema is transparent and descriptive. Column names are explained in natural language. And another interesting thing that helps a lot large language model is to link certain entities, certain categorical values that, for example, you can use in your tabular data sets to external ontologies. And those ontologies really represent your domain, represent the relationship between different entities, between different concepts. And if you link database entries to external ontology, it provides invaluable amount of additional information to large language model. Another point there is data standardization. For example, across hundreds of different tables that we're dealing with, date can be represented in multitude of different ways. So our organization is now going through a major effort of standardizing the way we represent things like dates, units of measurement, assigning data type constraints to the columns to make sure that every data set across different divisions and the whole universe of data that S&P Global produces adheres to the same standards. And then it's much easier for a large language model to interact with it and interpret it in a reliable way. And finally, last point is very different from the previous two. The previous two are very much intertwined with the data set structure, database itself. The last one is collecting those natural language queries that you can map to specific data entries. And what it really means is that we are working with subject matter experts who curate this data to understand what kind of questions you can ask of those data sets. And we need about maybe 50 to 100 questions, depending on the complexity of the database, to really have a good set of examples to show to the large language model what type of questions can you ask and what type of queries those questions would map to. For example, in the most traditional way, it would be SQL queries that retrieve the data that would answer those specific questions. So this is a very vital part, and it boosts the accuracy of retrieval models by almost 20–30%. So it's very important to do that step. All right, and in terms of data preparation for textual or unstructured data sets, that problem is considered to be simpler and kind of well solved. However, there's still a lot of limitations and improvements that you could do. Maybe you've heard about RAG approach, which stands for Retrieval, Augment, and Generation. It's basically you need to break your text into smaller chunks, let's say paragraphs, then convert those chunks into vectors through applying an embedding model that represent the meaning of the chunks, storing them in some vector database, and then at the moment when user asks a question, you compare the question and you find the chunks that are most similar to that question, you retrieve them, and you formulate an answer based on that. So this is the naive approach. It works so-so. It's simple to implement, but there's a room for improvement, as I mentioned, and there are scientific papers coming out more and more lately that this approach has a lot of limitations, and certain chunks can never be retrieved, no matter how you formulate your question, just because of the mathematical limitations of how these vectors and embeddings are generated. So we've been doing a lot of work and research in terms of how we can improve that side of things. And one of the simplest additions that helps a lot with the accuracy is enrich your chunks with metadata. That basically means that every time you retrieve a chunk, you retrieve certain entities or certain concepts from those chunks, and you put them in separate columns as metadata filters. Or you assign certain tags, for example, category, or some sort of classification that is useful for filtering in your domain. Or you could do other things with that, but it's basically retrieving most useful information from the chunk and making it easily available to a simple filter instead of encoding it within the embeddings of the chunk. You can also propagate document level information to the chunks, because document title will not be part of every chunk, but it might be very important for filtering. It could be the type of the company, the name of the company that document is about. That's also very useful to propagate on the chunk level. And the other two items are some innovative research that we've been doing at Kensho. First of all, figure extraction or chart parsing. There are a lot of charts and images within financial documents, and it's hard to represent them in a flat textual or numerical way for the LLMs to be able to interact with them. And you might say, well, LLMs are pretty good at analyzing the charts and telling you, what numbers, what colors, what categories. But when you run a more accurate test, you can see that they're not very accurate. And in financial domain, we cannot afford plus and minus approximate values. We need to be precise. We need to be exact with our numbers. And so we developed a custom model that parses these charts, extracts data, and puts it into a table. Very precise, very high accuracy, and no LLMs involved. It's a traditional neural model architecture, which is, at this point, previous generation of models, but still serves a purpose and works really well. And finally, table structure recognition. There are a lot of tables in financial documents. Sometimes they're huge, sometimes they span multiple pages, sometimes there are complex headers that have multiple levels within them, or columns split into subcolumns. There are all sorts of different things happening in those tables, very difficult to represent numerically. And what we did, again, we created a special model that recognizes the tables, and then we developed techniques that chunks and vectorizes the tables in a certain way. Not the naive way, what we do with texts, but the way that adds additional information to each of the chunk of the table, like header information, overall description of the table, and some other metadata that you can generate. And that also helped boost the accuracy significantly, especially on the documents that are heavily augmented by tabular information. All right, so these are all the steps that you need to do to both tabular and textual data sets to make them more accessible for LLMs. And now getting into the methods of access. On the tabular side, the two main techniques today are tools-based or API-based approach. This is a very old technique. We were using it back in Capital One and back at Nuance. You basically pre-program some certain logic for certain questions, and it's very deterministic and executable. You may be mapping some queries to specific parameterizable SQL queries. You pass the parameters, retrieve the data, run some custom logic, return the answer. Very old technique, but still very much useful because of its predictability and deterministic nature. And then very exciting new technique is text to SQL, natural language to SQL. There are different names to it. But you basically take the text and you generate the SQL query dynamically. What is very powerful about that is that you don't need to spend a lot of time trying to figure out what API routes do I need to build, what type of questions user might ask, what are the edge cases, how do I make sure that my coverage is adequate. You don't need to know any of that. Text to SQL model takes text, generates queries, especially in those cases when you need to do things like sorting, grouping, filtering. Those are very difficult to foresee and pre-program in the API approach, but very easy to generate dynamically. So we developed text to SQL approach, and our baseline had accuracy around 30-40% before we did any of the data preparation steps. But after we added machine readable metadata, make sure that data is standardized, and created a query bank using the examples of natural language queries provided by subject matter experts, the accuracy jumped to the levels of 80-90%, which is production grade accuracy. What I was very surprised because it was an experiment. I wasn't expecting any production ready results, but that's where we are, and these models are getting better and better. And some techniques are getting better and better in addition to the models. So now it's our go-to approach, and we're using it in production. And on the unstructured side, the main approach is retrieval augmented generation, as I mentioned, with some enhancements that we implemented. The accuracy also improved significantly there. But there's also GraphRock approach, where you try, instead of having your chunks as flat structure, you try to establish relationships between those chunks. So instead of retrieving just the most similar ones, you might traverse certain relationships in a graph, retrieve the nodes that are relevant to the chunks that matched your query, and that improves the quality of the answer as well. And if you see, I have hybrid option on both sides. That's really where the secret sauce is. When you combine different techniques with certain parameters, and through a lot of experimentation arrive to a good sort of logic between when you trigger one or the other, this is where you really achieve the highest accuracy you can get to today. And we are experimenting a lot with those hybrid agents, combining different techniques together. All right, so this is an example of hybrid architecture for tabular data retrieval. As I mentioned, the setup costs for APIs, designing those routes, understanding how users will interact with them, and really learning from that iteratively is a very laborious process. It's very difficult. There are a lot of edge cases. So it takes a lot of time to set it up. So what we decided to do is to actually always start with text-to-SQL agent. The setup cost is very low. It's the same approach on any data set. You quickly spin up text-to-SQL agent. And then you put it in production, and you start learning from how people interact with this agent. And this is where you can identify, okay, these are my most frequent, most in-demand type of requests. So I'm going to implement API routes for those. So gradually, most frequent requests that can be done by API approach can be transformed into API-based approach. And then you end up with a hybrid agent. And then you can have an orchestrator that knows what types of queries are handled better by one or the other. Or you can have something like, I send everything to API, but I fall back on text to SQL if API doesn't have the correct route or doesn't return the results. This is our go-to method today, and we are trying to scale all of our tabular data sets to use these data retrieval methods in our agentic architecture. All right, now I got to the meat of this presentation. This is the enterprise agent framework. We developed it specifically for S&P Global, but really what you see on the slide is applicable to any other domain or any other large, medium, small organization. The framework outlines a layered approach to how we build complex agentic experiences at an enterprise level in a federated and scalable manner. And federated is a key here because Kensho is a small company within huge organization. We cannot possibly build out this architecture for the entire enterprise. So we designed it in a way that there are ways of how the entire organization can contribute and be incentivized to contribute to this architecture. And you can see this as some sort of platform where consumers and producers of AI building blocks really share what they have and leverage what others have contributed to build these complex agentic applications. And what it really unlocks is a unifying intelligence layer that is cross-divisional and that connects all the divisional data together, which is, in our case, and I think in many other companies as well, I can speak for Capital One as well, is very difficult. For one division to get access to the data of another division, you probably need to go through multiple approvals, processes, and so on and so forth to just being able to access something. This platform makes it possible for anybody to easily come to one place and interact with all of the S&P Global data. And at the core of this design is Kensho Grounding Agent. That is the foundational layer for any AI system that needs to interact with S&P Global data, both internally and externally. And now we're going to focus really on the central part of this diagram to just not disperse your attention too much on all the elements around it. There are 4 layers. What you see on top, this is the result that we want to get. Those are the custom applications built for specific user personas, user profiles. Those are the things that interact with your customers, our customers. And there are all sorts of different applications there. There could be client-hosted applications. So our customers will build applications using the tools that we give them from depicted on this diagram. There could be agents that are built by Kensho. There could be agents that are built by our divisions. And there are also ecosystem partners. And that's a very interesting part. It really allows us to plug in our data into any ecosystem that our customer prefers. So we meet our customers where they are. We have announced an integration with Anthropic Finance, I believe on July 15th. It was huge. We got a lot of interest from all sorts of different companies that we haven't even worked with before, because we made our tooling available in the Anthropic ecosystem. We also launched our grounding agent in Google's agent space on October 6th, also very recent announcement. So now it's available for GCP customers as well. We are working with AWS, we are working with Salesforce and Snowflake and Databricks, with all of the providers which are, most of the widely used cloud providers that are out there. And we're making our data available there easily as a building block. Moving down, you see Kensho Grounding Agent. Kensho Grounding is really the orchestrator of a huge amount of data retrieval agents. And data retrieval agents are the agents that are contributed by the whole organization for different data sets. The bottom layer depicts our AI-ready data. It comes from different sources, but data retrieval agents are the experts for specific data sets. So for example, you could have one of the tabular agents, like text-to-SQL agent, that knows how to interact with specific group of data sets in the bottom layer. You can have unstructured data retrieval agent, and you can have many, many, many instances of those, which are created by different divisions, not by Kensho. Kensho's role here is to introduce standards, protocols, and make sure that everybody adheres to those, so all these agents are interoperable and can talk to each other and can work and plug in nicely with Kensho Grounding Agent. And some of the key principles here. So I've seen a lot of diagrams, similar diagrams from big companies like BlackRock, LinkedIn, Uber, trying to do similar agentic frameworks, but I have never seen anybody emphasize the importance of decoupling data retrieval from data manipulation. And normally, what is happening today, people build these big monolithic agentic experiences, and it's hard to track down if hallucination happened somewhere in the middle, if it didn't happen, how do I see where and when it happened? And what we learned is that it was very helpful to decouple data retrieval from anything else that your application does. Also, grounding agent returns granular citations, and it means that each data retrieval agent is required to provide pointers to where the data came from. That is enforced by our retrieval agent protocol, and it's a more restrictive protocol than protocols like MCP. So we make sure that each data retrieval agent can point to the source document and even page or part of the page where the information came from in case of unstructured data. And in case of tabular data, there are multiple ways of how you can provide the evidence, rows, columns, names of columns, or SQL queries. There are a few different flavors of how you can do that. And finally, we avoid LLM generation upon retrieval. This is how we decouple things. Once Kensho grounding agent retrieves data, it doesn't do anything to it. It returns it in a structured form with citations, nothing else, no answer generation involved, because this is where you introduce hallucinations. So we make sure that the data that we retrieve is reliable, accurate, and nothing was hallucinated and improvised in addition to that data retrieval step. It's very important for S&P Global because S&P Global is primarily data provider. We sell data, so we need to make sure whatever we sell is reliable, traceable, and there is proper lineage and provenance attached to everything we return. So why is all of this important? First of all, the layered architecture is important for us because we have customers with different technical sophistication. Some of them want to interact only with the top-level apps if they don't have technical teams, so don't have time to develop anything internally. That's normally the choice, the primary choice that they make. But there are also more technical customers that buy the data. A lot of business of S&P Global is just selling raw data. In this case, we started selling an add-on, an AI-ready data version for the same data set to those customers. And some people want to interact with our data in a conversational way, and this is where Kensho grounding agent comes in. They might want to build their own apps. They just want the data from us. They don't want anything else. So they integrate with Kensho grounding, and they can get any data that they need. And there are also data retrieval agents. You can integrate with each of them separately. Each of them are available through MCP protocol, so they're plug-and-play architecture. We haven't had a lot of demand for individual agents yet externally, but we do have certain scenarios internally where people prefer to go directly to the data retrieval agents instead of interacting with the orchestrator. So another important aspect here is high reusability of components by keeping, first of all, application logic separate. All the building blocks start from the second layer going down. All of this is in a way similar to microservices architecture, and I think that's the powerful, very powerful approach that microservices have become popular somewhere in 2015-16. And it really changed the way we develop software, breaking down the monolithic applications, allowing different teams owning different components. And in the context of large enterprise, it's vital to have this flexibility and being able to switch and deploy things independently. And finally, what matters most for my teams is the developer experience. It's much easier to troubleshoot, find issues, and figure out what went wrong when everything is decoupled and has its own login traceability and additional information that you can drill into. Now a quick example of how Kensho grounding agent really works. In this case, I have a question. Over the last quarter, how has ExxonMobil's stock price reacted to changes in the price of oil? Has Exxon's leadership commented on this? Very typical question that a company analyst might ask. And before, it might have taken, I don't know, days for them to collect all the information to be able to formulate the answer. But today, if you send this request to Kensho Groundings, first it hits the router, and the router job is to deconstruct this complex query into atomic sub-questions. And each of the sub-questions goes to a specific specialized data retrieval agent. In this case, we retrieve price of oil from oil price data retrieval agent, we retrieve price of stock from market data agent, and we look for leadership commentary in the transcripts of the earnings call. So all of this happens in parallel, then Groundings aggregates all the retrieved data, returns it in a structured format with citations. Again, no generation of answer at this point. All right, so that were the main building blocks. And as a recap, I want to point out what are the most important things that I've covered today. First of all, I covered the Kensho and S&P Global's journey from AI-ready data to agentic systems. Then we took a look at the AI readiness for tabular and textual data. We talked about specialized agents, which are the foundation components of future AI systems, such as hybrid agents powered by technology like text-to-SQL, RAG, and some other techniques. And then I introduced the enterprise agent framework that really embodies a comprehensive enterprise mindset, which is very important for our CEO. And thankfully, we have this top-down mandate to unite the enterprise and build this technology. Otherwise, it would be very difficult organizationally. We also talked about how this architecture allows federated and scaled development. And yeah, I just covered that point as well. Modularity and scalability, extremely important in the large organization context. And Kensho's commitment is to focus on standards and really drive this effort, but also explore advanced techniques and cutting-edge technology, share knowledge, and teach the rest of the organization how to apply those latest techniques to the tasks that they have at hand today. So that was all. And at this point,
thank you. Diana, let's give it up for Diana.